Okay, hi guys. We are going to be starting chapter 3 today. Kind of nice. Today doesn't have really a lot of numbers that are going to be involved, so that's kind of a nice break in algebra. Sorry, I need to get a straight edge out today. Okay, so today we're going to be talking about interpreting graphs, which we did back in 8th grade math, and you guys were pretty successful at it, so hopefully this shouldn't be too difficult for you. Okay, so first of all, vocabulary of the day. We do have two words that we need to understand, and one is continuous graphs and the other one is discrete. So for continuous graphs, okay, continuous graphs are graphs that are connected by lines or curves. So here's an example of continuous graphs. Okay, so continuous graphs, kind of one way that I remember this is you're going to notice in one of them, everything's kind of dots, and the other one, it's a connected line. So if we have dots, it's going to be discrete. And if it's connected, it's going to be continuous. So it starts with the same letter. Okay, so connected graph means continuous because they both start with the letter C. Okay, and then we have discrete graphs, which are going to be like the ones on the left here. So if it's a dotted graph, it's going to be discrete. Okay, and the difference between the two is, do we have individual data with no decimals or fractions in between, or do we have continuous data, which is going to be like measured data? Okay, anything that we measure, like temperature, could be continuous because it could be a decimal. There's always numbers in between whole numbers and other fractions and decimals. Other ones would be like weight is a measured unit, so that would be continuous. Height, those kind of things, anything you can measure. Okay, discrete is going to be counted data. So if I'm talking about how many students ate hot lunch yesterday, that would be a discrete number because it wouldn't ever be like 2.5 students. It would always be 2 students or 17 students or whatever. So if it's counted data, it's going to be discrete and they're going to be individual dots. If it's measured data, it's going to be connected, which is continuous. Okay, so here's an example of just interpreting the graphs. So it says each day, several leaves fall from a tree. One day, a gust of wind blows off many leaves. Eventually, there are no more leaves on the tree. So here, we always need to take a look at what the graph is talking about. So we're going to look at the axes. So this is how many leaves there are over time. All right, so leaves over time, you're going to see here, this one is showing an increase, okay? As it's going up, that's an increase in the number of leaves. And then horizontal line always means no change. Okay, so what's going on here is we're increasing the number of leaves. So the tree's getting more and more leaves, and then it stays the same for a while, and then they drop off, so there's eventually 0 leaves on the tree. Okay, and that's not where we're at here. Okay, here it's talking about the leaves are falling from the tree to start, so it can't be this one. Okay, so both of these start with a decrease in leaves, which is what this first part says. And then it says, one day a gust of wind blows off a lot of leaves, and eventually there are no more leaves. So this graph here shows that there's a time where there's no change in the amount of leaves, so the number of leaves would stay the same. And we don't ever have that. Here we have some leaves falling, and then all of a sudden it blows off a ton of them, and then there's none. Okay, so we never have it stay without any change to the number of leaves, so we're going to eliminate that one. So here's what's happening. Several leaves fall from a tree, and then all of a sudden we get this gust of wind, which blows off a lot, and that's why it's going to go steeper down, because that change is happening faster. And then after a while, eventually there's no more leaves on the tree, which is why it's down here. So this answer here would be graph B. Okay, here's another example like that. So it says the air temperature increased steadily for several hours and then it remained constant. At the end of the day, the temperature increased slightly before dropping sharply. So here's another word we need to notice. Remained constant. Okay, so remain constant is when we have no change, staying the same. So do any of these have remain constant? Well, here they have it remains constant, and here it starts constant. Here we have it happening a couple of times, and here we have it remaining constant there. So let's read what's happening before. First of all, it increased steadily. So at first, it's increasing. Does this one show increasing right away? No, it shows it remaining constantly right away. Does this one show that it's increasing right away? Nope, it shows that it's remaining constant. So it's going to have to be this one. Let's just double check. So it increased steadily for several hours and then it remained constant. So that's why it's got this horizontal line here. At the end of the day, the temperature increased slightly, and that's why it's going up, and then it dropped sharply. So it came back down. So that's exactly what's happening in graph C. Okay, so in the next part, we are sketching a graph for the situation. So if you could, when you do this, try to use a straight edge. That would be really helpful. If you decide to use DocHub, there is a straight line tool that you can use in there also. Okay. Everything that we're going to be graphing today is going to be positive values. So all of our graphs are going to be in, excuse me, in the first quadrant. Okay, so it says a truck driver enters a street, drives at a constant pace, and then stops at a light and then continues. So the first thing we have to do is identify our two variables. What are we going to list this? Okay, a lot of times it's time across the bottom. So this really is, what we've got here is this speed is what we're talking about, right? Speed over time. So we are going to label this bottom part of the graph as time. Time always goes on the x-axis, and then speed is going to go on the vertical axis. Okay, time is what we call an independent variable. That means it doesn't change for anything. Time just keeps marching on, right? Independent variables always go on the horizontal axis. Okay, the speed of the car depends on what time we're at. So the truck driver enters a street. So before they enter the street, their speed is probably down here at 0. Okay, so that as they enter the street, their speed is going to increase, right? So for an increase, it just has to go up and to the right. Okay, that's showing an increase in speed for a while. Then it says they drive at a constant speed. So constant speed, again, means we're going to draw a horizontal line because there's no change. Okay, and then they stop at a light. So when they stop at a light, what happens to the speed? It gradually slows down to 0. So this part is going to have to come down all the way to 0. Okay, and then they're going to continue. So as they continue, what's going to happen is they're going to speed back up, probably until they get to about that speed again, and then they're going to continue from there. Okay, so notice that I don't have any numbers on the graph, and that's totally fine. We're not really concerned with at exactly what time were they at what speed. We just want to see a physical representation of what's going on. So the last part says, tell whether the graph is continuous or discrete. So I could have told you this before even making the graph. Here we're measuring speed. Speed is something that is constantly changing, and it's not always necessarily exactly 25 miles an hour. It could be 25.2 miles an hour. So anything that could be a decimal answer is going to be continuous. Okay, and we did connect those dots. It made sense to, because it's not stopping and starting along the way. So when it's connected, it is continuous. Okay, the next one says a small bookstore sold between 5 and 8 books each day for 7 days. So again, we're going to make a graph in the first quadrant. And this one, it's going to be time in days. And I'm actually going to go ahead and label this. This is for 7 days. So I am going to go ahead and number this graph. Oops, it's kind of squished in there. Okay, and they sold between 5 and 8 books. So if there are numbers in the problem, we probably should have numbers in our graph as well. So here we're talking about the number of books that we sold. So I'm going to label this part number of books. Okay, and it's between 5 and 8, so I guess I'll just kind of count by ones. Okay, so this one is a little bit tricky because it doesn't say exactly how many they sold, so we can just kind of make this up. But the real important concept here is this going to be discrete or continuous? Okay, when I'm talking about number of books that I sell, could I ever sell like 7.2 books? And the answer is no. Okay, this is counted. Number of books that we sell is counted. So this is going to be discrete, which means we're only going to put dots on our graph. We're not going to connect it at all. So on day 1, they sold somewhere between 5 and 8. So it doesn't really matter where we put that dot. I'll just kind of put it at 7 just to pick a number. Okay, and we can do that for each of the 7 days. Doesn't really matter, somewhere between 5 and 8. So I'll just pick numbers there. Anywhere from 5. We definitely need to hit 5 and 8 at some point, but here's 6 and day 7. Okay, that's all there is to that one. Like I said, it's a little tricky because they don't give you the exact numbers, but the important part is knowing that it's discrete data because you couldn't sell a fraction or decimal number of books. Okay, Jamie is taking an 8-week keyboarding class. At the end of each week, she takes a test to find the number of words she can type per minute, and she improves each week. Okay, so weeks is going to be one of our variables. So the amount of time in weeks is going to be here. All right, and then it is an 8-week keyboarding class, so I should probably put numbers for that. If you have graph paper at home, you could certainly use that to make it look a lot nicer than I'm making it. But for today, it doesn't have to be exact. So this is fine if you don't have graph paper. So it says at the end of each week, she takes a test to find the number of words she can type per minute. Okay, so going up the graph here is going to be words per minute. All right, and all it tells us, it doesn't give us any numbers, it's just saying that she improves each week. So number of words per minute, again, that's a counted thing. She's not gonna necessarily be, number of words is always counted. So how many words can she type in 1 minute? They're always gonna give you a full number of words. Like even if you are on a word, they're not gonna say you could type 36.2 words per minute. They're going to say you only hit 36. So this is going to be discrete, okay? We're going to use dots because it's a number of words per minute that's not a fraction or decimal. So it's just saying that she improves each week. So let's say week 1 she's here. These just have to slowly or steadily improve. Every week that dot needs to be higher than the one before. They don't have to necessarily be in a line. Maybe in week 4 she takes a bigger jump, and then in week 5 she doesn't improve so much, but it's still higher. It doesn't have to all be in a line, but it's just saying that she's improving each week. Okay, so there's an example of what this one could look like. All right, the last one says Henry begins to drain water tank by opening a valve, and then he opens another valve. Then he closes the first valve, he leaves the second valve open until the tank is empty. That sounds really kind of confusing, but again, we're going to be talking about how much water in the tank is there over a certain amount of time. Okay, so down here we're going to have our time, and it doesn't really talk about minutes or seconds. We don't really have to worry about that. And then it's how much water is in the tank is going to be the other one. And they don't give us any numbers to work with here in this problem either. So therefore, I'm not going to put any numbers on either axis. Okay, so the start is going to be along the y-axis here. I don't know how much water is in the tank, but I'm just going to put a dot up here somewhere to start with, how much he has to start with. Okay, so he begins to drain it. So the amount of water in the tank is going to go down, right? So he opens one valve. So it's starting to drain, it's going down. Okay, then after that, he opens another valve. So when you open a valve, that's going to mean it's going to drain faster because you have 2 valves that are open for draining. So now, instead of being at this slope, we need to make it go down steeper because it's changing faster. Okay, after that, he's going to close the first valve. Let's see here. So when he closes one, it's going to slow down. And then he's going to leave that other one open until it's empty. So it's going to slow down again, but it's going to go all the way down until it empties, which means it's going to reach 0 water in the tank. Okay, so hopefully this should be kind of easy for you to understand because we did a lot of this last year and you guys were really good at it. So let me know if you have any questions on the 3-1 worksheet, and we'll see you later.